we are very near the end of the semester, and what we are learning about this universe is getting more and more amazing. This chapter, chapter 29, is on the Big Bang. But we will have one more lecture to go next week on cosmology to wrap up the semester. We will complete our current understanding of the universe by then. Here you're looking at the James Webb illustration and the Pathfinder model that was once here locally in Greenbelt's Goddard Space Flight Center. I believe it is now in the UVA Hazy Center in Chantilly, Virginia. You can go visit that if you have time. James Webb was finally launched in 2021 on Christmas after many years of delay. About this lecture, number one, I would like you to watch the video Runaway Universe before moving on to part two. This will make it flow a bit better. It will also save you some time next week because you will need to watch it for homework in any case. And number two, because many facts and ideas are all connected, this is why you should watch Runaway Universe after part one. And much of the materials, we are really just presenting it for the next week as well. Number three, we will present some important concepts in this lecture so that we will tidy up many loose ends and you can have a better grasp of the big picture. I point out this week's lecture and videos provide an overview while avoiding much detail. So pay attention not to the detail, but to the big ideas and the big picture we are trying to understand. Okay, number four, I will provide additional lectures in the final week on cosmology. And so next week is when we will put the story of the universe neatly together. Okay, just keep that in mind. Number five, this lecture and what follows are the big ideas you should know. I repeat this again. I am going after the big story about this universe, and it would be a shame if you miss it. I hope I can deliver it with enough clarity to let you see that universe is wild beyond imagination. Many mind-boggling discoveries happen only in the past 25 years or so. So you are kind of lucky to be in this young generation to learn about the things that people have struggled through before. And even if much of these materials are not tested, for you, it would be worth it to know about these progress simply as a person living in the present time. Okay, so take it seriously. I think it should benefit you to have this knowledge. Let's have some quick history. Galaxy recessional velocities were observed before 1927. And number two, George Lemaitre theorized an expanding universe even before Hubble and laid down the idea of an early universe and an estimate of the expansion constant. It just was not well known, okay? And then Edwin Hubble came along in 1929 and shown the official data. But in reality, other astronomers have already done it as well. The idea of the universe's expansion was hard to accept. I'm sure folks were wondering if that was some local effects or some similar errors or whatever. And even as late as, say, 1950s, some people are still not really accepting it. And for example, Fred Hoyle was a very prominent astronomer, and he did not believe it. His idea was that of a kind of a steady state universe, and he mockingly called the idea a Big Bang, right? He thought it was kind of a derision, okay? And so the Big Bang, the term came from Fred Hoyle, who was making fun of it, and that term got stuck. And number five, IAU voted to rename the law to Hubble-Lemaitre Law in 2018 because as we go back to history, we realize there's a lot of things that were missed. So let's do another quick review of the Hubble plot, which is shown in late 1920s. Astronomers observed recessional velocity, basically just velocities using redshift, with respect to distance, and the result was a straight line. The galaxies observed at the time were of course considered very far, but only at about 0.1 redshift away. by today's standard, that's actually quite near. And now, by today's standard, we are looking way beyond 2. Okay, so 0.1 was very, very small. But the distance scale of 0.1 redshift was enough to display a clear trend. So keep in mind, a universe is huge. So even z equals 0.1 is quite a large distance, okay? And remember, redshift z is related to the velocity. The greater the motion moving away from the observer, the greater the redshift. A blue shift is moving toward the observer. So the observations of redshifting galaxies all over means that galaxies are moving farther away. And the farther away a galaxy is, the faster it is moving away. And you will do, as you will do in the lab, the redshift z can be converted to velocities in a very straightforward fashion. And you may recall that the slope of a line in algebra is rise over run. In this case, the rise is the change in velocity, and the run is change in distance. So this means the slope, we coined the term h naught in units of velocity over distance, and this is the Hubble constant. Here the units are kilometers per second per mega light years, okay? The current value of Hubble constant is around 22 kilometers per second per mega light year. We can also use megaparsec instead of mega light year, and that value has been consistent around 67, okay, 67 kilometers per second per megaparsec. And we tend to use megaparsec actually, and this is also true for our labs using Stellarium, so just keep that in mind. However, just recently in 2025, 2026, the latest careful studies puts the value possibly above 70 kilometers per second per megaparsecs, more like 73, and that is on the high side. And this create even greater this issue, what we call Hubble tension, which means that somehow the disagreement between different sets is becoming even greater. Now, one very logical consequence of the Hubble expansion, and if you just bother to think for a moment, is that the universe expanded and expanded, and so the universe must have been smaller and smaller going back in time, okay? And then we are faced with a very strange question. How far does that go to in terms of going back? And what was the starting point? So if we take Hubble's law on face value, that the universe is and has been expanding, then this extrapolation backward leads to the thought of the universe starting as a point from the very beginning. But some scientists objected to the idea. Certainly, scientists are smart enough to always come up with alternative to explain the observations. Indeed, the idea of an expanding universe was mind-boggling. It was just hard to accept. A person of good scientific mind can say, well, that's what we see now, but that may not be the case before, and that is a completely legitimate argument, okay? And indeed, it will take more time and more observation to settle this issue. As of today, literally many decades from 1920s and 1930s, everything we observe is that of Hubble expansions. And in fact, even more, and we will learn what more is to come. And yet, isn't it strange somehow to think of universe as having started like a single point? That is a very strange notion, isn't it? No matter how factual the observations are, the idea of a singular point beginning, it is really beyond understanding. So that's why it is just hard to accept. Even with the wildest imagination, scientists will just find it difficult to believe that is the reality we are seeing, because we just cannot understand how the beginning state of the universe could be like a point. It could be, how can that be physically sensible? Okay, so that was at least the thought for many, many decades. And so scientists, even with the wildest imagination, do not go around claiming wild outcomes as true. In general, we are very careful to declare the truth. Fun conversation over coffee or wine or cheese are not the same as having more data and incontrovertible proof. Okay, so if you read a little bit of history on this issue, say in 1930s and 1940s and on, there are records of many papers and debates, and you will see indeed various thoughts on this. Is by no means an easily accepted argument. Okay, in any case, the idea of Big Bang, although amazing, continued for a long time to have doubters. Okay, to have doubters. But if you take it at face value and you believe in an expansion, and you believe in an expansion to have gone all the way back to the very beginning, then you are facing a question of that singular beginning. And you will ask, what was the universe like when it was a baby at the very beginning? Okay? And so, the idea of Big Bang was just not easy to accept. Again, jumping for many decades, with more observation of earlier universe and farther distances, Big Bang is eventually accepted as the correct reality. As much as it is difficult to accept, there comes a point that all data, all observation just overwhelmingly point to Big Bang. Okay, there are always opponents as well as proponents, and that is simply because scientists as a group explore all possibility and see virtues of different ideas, and that's a good thing. Okay, it's not necessarily a bad thing. And I just mentioned Fred Hoyle in 1950. The very prominent astronomers did not like the idea, and he's a proponent of an idea that's closer to a steady state universe, no Big Bang. It is said that he coined the term Big Bang as a mockery, but the term Big Bang got stuck. Apparently, it sounded pretty good. Now, I myself thought the word Big Bang sounded pretty cool. All right, so I myself like it. But in any case, Big Bang wasn't just talk, fancy talk. There were some early and pioneering work on it. Okay, real work, real physics and astronomy ideas. For example, some really smart people in Princeton University in the 1950s started thinking from the ground up, and they are the pioneers of Big Bang physics. No one before them had even thought about this or knew how to even tackle this issue. And so these people have to start from the ground up and start learning how to do these for themselves. Okay? All right, so these are not just fancy talks over coffee, right? Scientists is all about real work, establishing physical principles, building up models, explore the formula that is correct, do some calculation, make some prediction, and so on. Okay, that's real work. And keep in mind this again, there is no direct observation of Big Bang. Hubble plot is a velocity versus distance plot of galaxy. It is itself not a direct observation of Big Bang. Big Bang is a conclusion if you extrapolate and believe in what you see. And that's why some scientists could argue otherwise, that there's no Big Bang, and argue that there are other possibility, okay? Just because the plot doesn't really show that, okay? But over time, as we understand physics and astronomy better, we begin to really get a handle on the issue. For example, we began to nail down elementary particle physics in 1970s. And from that understanding, we strengthen our view, such as from the particle physics knowledge, we build up the particle production processes in the very early universe, and it was just correct, okay? And certainly our understanding of the Big Bang has been built up slowly, step by step. Not only we have to figure out more, but we have to learn more physics and more astronomy in order to know what more we need to understand. And that was done over time in the past 80 years or so. So here, Big Bang is an example of scientists pursuing an idea based on strong imagination, but not a blind one, okay? But on very strong understanding of the physical principles that we have come to know, and that it is how progress is made. And history is indeed full of world-class scientists, like these people in Princeton that have done amazing work that, you can argue that's almost on par with Einstein, maybe not like Einstein, but maybe within ballpark, okay? And indeed, history is full of very, very accomplished scientists. So let's go through a very basic discussion of thinking the Big Bang from very basic physical principles, and not just talking the fancy talks, but applying principles to see if we can figure out at least some basic features, okay? If we believe in the singular beginning of the universe, then we can roughly have an idea of the expansion with time as shown, just for illustration, as shown in the slide here. In terms of the temperature of the universe with respect to time, the beginning must be very, very hot. Now, we don't know how hot it is, so we're not going to show you anything but a straight line curve. It's just representative, that's all. How much hotter, again, we do not know. But we will figure out later. Right now, we're just trying to understand the big picture. But at least we know it is much hotter than now to start, right? Because expansion means cooling has happened. So because the universe expands, the space increases and the energy per unit volume decreases, okay? And this is because we are not assuming new energy is being generated out of nowhere. So right from the start, we actually have to believe in some strong physical principle, and that is conservation of energy, sort of. We just do not believe that energy can just pop out of nowhere, even though in the very beginning, you questioned about Big Bang. And the beginning is always a question, but once that happened, no new energy. So whatever the energy the universe had at the beginning is the total energy that the universe will have afterward, all throughout the expansion stage. Okay, so just think about that. So this conservation of energy principle is a very strong one we hold on to, from which we can figure out many facets about the expansion of this universe. And hence you see this plot. Because of that principle, due to expansion, but the same total energy, you see the plot decreasing, a steady decrease in the temperature of the universe. The energy per volume is decreasing, and hence the background temperature is decreasing. You see, just like that, just applying basic high school physics, you cannot really figure out something about the history of the universe. And as the universe expands, the universe cools. And now we will put some details into it, and this requires some expert knowledge far beyond high school. I'm careful to tell you that I'm showing you this to let you know the complex science that goes into each stage of the universe. But it's still a very rough and quick overview, and this chart is just an illustration, and please do not worry about the specific numbers or the detail, okay? What I want to tell you is that physicists and astronomers have been researching hard for the past century. We know very well what processes occur under what temperatures and under various conditions. We know these processes because of all the research and all the money and effort that we invest in understanding them, like nuclear physics, elementary particle physics, thermodynamics, and so on. Okay? Now, I'm sure, as an example, you heard of particle smashers or particle accelerators, like the ones in Fermilab, Chicago, or CERN in Geneva, Switzerland. These are examples of some testing grounds of many basic physics law that we came to know. And if you just look at this chart right here, just look at the temperature scale, okay? It goes from 0 to 10 to the 31 Kelvin, over 31 orders of magnitude. And recall the core temperature of our sun from chapter 6. that is about 20 million degrees, okay? And where is that? That's about 10 to the 7 right here. So you see, it's not even close. The Big Bang temperature, okay, we are talking about a billion, million times hotter, all right? The layman's statement is that Big Bang physics is far more powerful than nuclear physics. Now, this dark region right here, the initial one right here, is around 10 to the minus 43 seconds. It's what we call Planck regime. In this earliest stage of the universe, we fully believe it is the realm of quantum gravity. No laws that we know now, even particle physics, would apply at this extreme high, extreme condition, high temperature, high density. And we still have no definitive theory on quantum gravity. And so this regime remains uncertain, and we have no way of doing any real calculation to figure out anything definitive. So far, we do a lot of speculative work based on the best that we know, but no one's going to claim they are the truth, okay? But we do know this, that once the universe expands and cools enough, various physical principles that we know will emerge, and these we can apply and understand. And thus, we are able to reconstruct a very good picture of the very early universe in some of the Big Bang stages, okay? And they are pretty good reconstruction. And let me point out specifically to the radiation era right here, from 10 to the minus 33, all the way down to about 10 to the minus 10. This is still a minuscule fraction of 1 second, a very tiny part. And that not even so long after the initial bang, the universe has already moved into the radiation era full of energetic photons. And the condition is so hot, the nuclear force is not yet allowed to take hold. The nuclear force, however strong, is still not able to hold such thing as quarks together because it's just too energetic, okay? And yet, as the universe cools further, let's say by a millisecond after the Big Bang right here, it's still quite a short time. Nuclear forces then can begin to form nucleons like proton, basically allowing quarks to bond, okay? And later on, as universe cools even more, atoms will form because we know atomic physics will be able to operate around that time, okay? So all this right here, all in this era right here. We will go into all this more detail next week. And so therefore, as you know, as you can see right now, there's a sequence of steps that the universe is going through very quickly in the initial time, setting the conditions until hundreds of millions of years later, when the matter can actually congeal together, and begin to form galaxies and stars. And as stated, we will discuss more of this next week. Here I illustrate some specific quantum processes with elementary particles at around 10 to the minus 2 seconds. Here, look at the first one. This is what we call pair production, with two energetic photons interacting and produce an electron-positron pair. Okay, so two energetic photon generating electron and positron. And these production rates can be calculated from quantum physics. Okay, they are just not fancy talks. They're actually calculable. And positron is the anti-particle partner of electron. Every particle has an anti-particle partner, and electron's anti-particle partner is the positron. And just for fun, I point out, electrons are stable and live forever as far as we know, okay? Not quite, but practically. But positrons are not really stable and can disappear and annihilate, okay? So we can ask the question, why there's an imbalance of electrons and positrons in the universe today. Astronomers may not ask these questions, but physicists do, okay? And questions like this, it's important to understand that it has implication on the condition of the universe that we know today, okay? And if you study this field, physics astronomy, you will be exposed to many similar questions that you typically do not hear in the public, okay? And many educational videos, such as NOVA, will point out these questions as well, such as when Stephen Hawking appeared in a video series, Stephen Hawking's Universe. I don't know if you ever heard of that series. For a while, that was quite popular. Okay, now moving on to the 3 minutes mark right here. And remember this 3 minutes mark, okay, for next week as well. Particle fuse to form helium and deuterium through nuclear forces. Okay, this is there is a seed of proton and neutron already in existence earlier, and they can capture one another to form more complex nuclei. One proton and one neutron is deuterium, and it's an isotope of hydrogen. Two protons and one neutron is helium-3. Two protons and two neutrons is helium-4. And by the way, helium-4 is the most common form of helium. And we are talking about 99.9999% of helium. And helium-3 is only a tiny, tiny fraction. And all this is also calculable from basic physics. And again, that will be discussed next week. And I will emphasize that all the hydrogen and helium in the universe is made in this early 3 minute stage of the universe. And stars do make a certain amount of helium. Stars do make helium, but the amount is not close to the existing abundances, okay? So effectively, all helium in the universe is from this early 3 minutes. I point out that the early universe, also generates some traces of higher elements like lithium, but just very, very minute. Okay. Now, in the third illustration, hundreds of thousands of years later, the universe is finally cool enough for electrons to join positively charged nuclei to form atoms. And this formation right here, when electron joins the proton, okay, this formation is also the reason for the cosmic microwave background formation, as now finally electrons and photons are no longer interfering with one another. Okay, and we will talk about the cosmic microwave background in sufficient detail. Okay, but this is just a preview. Now here, from this point on, photons can go on traveling and electrons can join nuclei to form atoms. They can now go on their separate ways. And so next week, again, we will say more about these. So it is good that you are exposed to these ideas now so that next week's presentation will not be too overwhelming. Here is a rough description of the stages in the very early universe, and I will just read it as it is. 1, the universe cools as it expands. Number 2, the early universe was so hot it contained mostly radiation, plus some elementary particles. Certainly there are elementary particles like electrons and positrons, but the simplest statement is that they are not in a stable condition. For example, electrons can be annihilated. We do have to consider dark matter in the mix. That although we do not know how much about dark matter and how it was produced in the early universe, nevertheless, dark matter was already present in this stage, and the gravitational impact of dark matter must be accounted for in any cosmological model. Remember that dark matter is the dominant form of matter, and in the early universe, its gravitational effect far outweighs all other elementary particles like electrons. Okay? Number 3, the hotter the universe was, the more energetic were the photons available to make matter and antimatter. Okay, that's part of the particle reduction process that we come to know. Number 4, protons and neutrons form as universe cools because of nuclear forces. Number 5, Fusion reactions produce deuterium, helium, and lithium nuclei, and actually some other trace elements as well. And nuclear forces are allowed to take over in so-called Big Bang nucleosynthesis, or BBN, right here. And BBN is indeed one among the work done by the Princeton physicists I mentioned earlier. They construct a chain of events which laid out the basics upon which we build up the full BBN model that we have today. It's very complete as of now. And BBN is one of the most important observable results, testing our understanding of the early universe. Of course, if we have these model of how much these elements were produced in the early universe, well, they better agree with what we observe, right? And they do, okay? Now, given the fact that these Princeton physicists did this work in 1940s, their work was so amazingly right on, almost prophetic, that I think they deserve a Nobel Prize. But of course, it doesn't always work that way. By the way, I point out that electrons and positrons are elementary, meaning that they are really the smallest units with no composite components. But protons and neutrons are made of quarks, which means quarks had to be produced in earlier and harder times, okay? So there are many more details like that, but you don't have to worry about these details. It is perfectly fine for this level. We just want the big picture, and we just have to skip a lot of details. We are making a big jump to 300,000 years ahead after the Big Bang, so that we can talk about the cosmic microwave background. In slide number 8, we already mentioned the event when electrons join nuclei to make neutral atoms. This has very important testable consequence. Well, all theories and models must be tested, and that means they must have predictable outcomes that can be observed or tested. This period of about 300,000 to 700,000 years is the origin of the cosmic microwave background that was discovered and stunned the world when finally observed in full glory around 1990. And we will go through its brief history later on. During this early period of 300,000 years after the Big Bang, the universe has cooled down to roughly 3,000 Kelvin. And that is still very hot for us, but it is sufficiently cool enough for neutral atoms to form. Electrons, through electromagnetic interactions, will be captured by positively charged nuclei. Almost all nuclei are single protons or hydrogen nuclei. So stable hydrogen atoms are formed during this period, and they are stable. Okay, basically an electron and a proton forming a neutral hydrogen atom. Now, because of cooling, photons are no longer energetic enough to knock off electrons from their orbits consistently. But there's another side to this formation of stable hydrogen atoms, and that is photons are also not being interfered with, right? And that's the other side. Before, the universe was hotter. Electrons are too energetic to be captured. Also, photons interact with electrons so much that they will knock off any electron of any hydrogen orbits. And that's why the hotter universe before will not have any hydrogen atoms or any neutral atoms at all, just because of the high energy and a lot of kinetic collision and so on. But now, as the universe has cooled down enough, electrons and photons are no longer interfering with each other. So the other side of the story is this. Photons can actually travel through the soup of matter without being blocked and interfered with by electrons. They can travel through space now and will continue onward for the next 13 billion years. Okay, now what did this mean? The universe becomes transparent in the sense that these photons then can travel through space and be observed by, for example, astronomers. these background radiation from the Big Bang has been freely streaming across the universe since atoms formed at temperatures around 3000 Kelvin. All right? These photons are the cosmic microwave background, or CMB, left over from the early universe more than 13 billion years ago, and they contain information of the early universe around that time. Now, what is the most important is that the cosmic microwave background can be observed. Okay, with our detectors, we can capture these CMB photons, and literally, when captured, these photons die. Photons are not solid objects that can be captured and then released. Photons are simply absorbed. Okay, so they are gone. So after more than 13 billion years of journey, the CMB photons measured by our detectors met their ultimate fate, and are gone. Well, kind of a poetic ending. And you can ask the question, how young was 300,000 years in a time scale of 14 billion years? Well, think of a human being and think of a baby. It is like a baby that was just born less than 1 day, okay? That's how young 300,000 years is in the age scale of the universe, okay? And this time period is a very important mark in the history of the universe. After this, visible matter can now begin to clump due to gravity, because now, atoms are forming. They are no longer being bombarded by photon and, being equalized in the sense of being smoothed out and being uniform, okay? And so right now, gravity can take over, and the matter will now begin to clump. Galaxies and stars will form later on. The first detection of CMB was in 1965 by Penzias and Wilson. They were working with a radio antenna horn with AT&T Bell Lab in New Jersey for communication technology, using radio waves bouncing off Earth's ionosphere. And you see a radio horn in the background of this picture is rather large because the radio wavelength is of the order of meters to millimeters. And they were receiving this constant background hissing in which they cannot remove no matter what they do. Reset and tune the equipment. They cleaned the radio horn, including the pigeons in them. They pointed the horn in different directions, and nothing worked, okay? And finally, they accepted the result and published a paper documenting this observation with very modest descriptions to the effect of excessive noise in the background, and nothing too spectacular. Yet, it was soon recognized as a confirmation of the cosmic microwave background, leading to a Nobel Prize, okay? The hissing was cosmological, okay? Cosmological. And now I'm going to emphasize the word cosmological, meaning of the universe itself, not of any single source, not a point source. Specifically, the hissing comes from every direction. Repeat, all directions. So this cannot be from a single star or a galaxy or even a very large regions. Okay, it is simply something completely filling up the universe's background everywhere. So when we say an astronomical source, we mean it is one object or a specific set or a specific region. When we say cosmological, we mean not a single source, but of the entire universe. The cosmic microwave background is a cosmological phenomenon, okay? Even though the paper was modest and simple, but it clearly laid out the detection of a cosmological signal. The implication cannot be bigger, and it was quickly believed that background is the remnant from the baby universe long time ago. Now, the Princeton physicists I mentioned earlier were working on this idea, actually very close down the road in Princeton, right? And Penzias and Wilson quietly made the discovery, completely independently, nothing to do with him. By the way, that radio horn that you're looking at, it is still in New Jersey. Now a preserved monument in a park. We will jump ahead to Kobe satellite launch in 1989, WMAP in 2001, and Planck Surveyor in 2009. And after Penzias Wilson in the 1960s, and long before 80s, in this period, much work on the CMB were done in a simple matter, such as balloon missions in the upper atmosphere to gain samples of the CMB. These work were enough for the specific instrument design of the first satellite, COBE, C-O-B-E, tailored to detect the cosmic microwave background, okay? Now, and I believe this plot you're looking at is not from COBE, it's actually from Planck, the latest generation. And I know that just by looking at the details. But the first stunning result was actually from the COBE satellite way back in early 1990s, showing a similar result, even though not as detailed, okay, but it's going to show the same curve and similar match. One of the instruments on COBE was to capture the thermal spectrum of the cosmic microwave background. The principal investigator or the leader of that instrument was John Mather, and you can look him up, John Mather. He won a Nobel Prize for COBE measurement of the CMB temperature spectrum. Okay, you can look him up. And look at this plot from the Planck Surveyor, showing the spectrum data completely matching the theoretical prediction. Basically, COBE showed the same thing, but here in the Planck, many years later, almost 20 years later, right? It shows basically the same thing, but just much more detail. And you see the red curve, which is the theoretical curve, versus the data, and the data are the boxes. And just look at how perfectly they match. Okay? Now, to explain this, let's go back to chapter 6, in which we discussed the solar spectrum being close to a black body spectrum. Our sun is actually pretty close to a black body. And what's a black body? The black body is an ideal case of a perfect emitter and an absorber of light. And that can be worked out mathematically to have a specific shape, and called Planckian shape. And by the way, the name Planck is everywhere because he's considered a founding father of quantum physics, okay? And we have shown that our sun is actually a pretty good black body whose solar spectrum closely resembles the theoretical black body shape. We have shown that before, okay, if you remember. It's not perfect, but pretty good. The emission peaks somewhere in the lower wavelength, and then the spectrum tails off towards the higher wavelengths, just like what you're seeing in this slide. And this is a very typical shape, a Planckian shape of a black body spectrum, okay? And here you see that this is a perfect match, okay, for the CMB between the theoretical curve and the measure spectrum, the measured data. The predicted curve is specifically calculated for a thermal background with temperature of 2.73 Kelvin, meaning that the cosmic microwave background as of now has cooled down to about 2.73 Kelvin. Remember, it was really hot before, but as the universe expands, the universe cools. These cosmic microwave backgrounds will cool with the universe, okay? It's now cooled down to 2.73 Kelvin. And you look at this shape, it is a perfect Planckian shape, as perfect as possible, okay? And each box, each square box, the black box that you're looking at, is the measurement of the energy flux at a particular wavelength by one specific detector set of the instrument, of the satellite, okay? And you are seeing this Planckian shape, this perfect black body shape because the early universe was a hot primordial soup with tremendous temperature, but nearly uniform everywhere at any stage of the expansion. Repeat, with temperature nearly uniform everywhere. Okay? Now, this nearly perfect uniformity in temperatures means that the basic thermodynamics was under as nearly an ideal condition as possible. It is ideal, okay, as ideal as possible. So the thermal variation or temperature variation will be close to the ideal case, which is black body physics. The ideal thermal uniform background of anything, okay, if something has like this perfect ideal temperature variation, ideal, in the ideal case, it will be a black body spectrum, okay? And this is why you see this, all right? So let this sink in for a moment. What we are seeing in this plot is the condition of the universe as it was now that we are measuring it, okay? This is not just a beautiful poetic statement. This is scientific result. Quantifying the condition of the early baby universe, and it was perfection. Well, almost perfection, okay? Almost. It is said that this is the most perfect black body measurement ever made. No objects, not our sun, nothing comes close to being this good, being this perfect of a black body, okay? And that's how uniform, how good of a behavior the early universe was in order to have results like this, okay? And this was stunning. Although we kind of expect a great result, we did not expect this in 1990 when Kobe result was first shown, okay? The perfect match blew our expectation out of the water, okay? And that was in around 1990. But again, I clarify to you that what you're looking at right now is the Planck surveyor around 2010, not Kobe, okay? After 2010, okay? We're just showing you this one, but the earlier Kobe result in 1990 or so will show you similar things, and that is when it stunned the world. What I have just shown you is a spectrum plot of CMB, but not an all-sky map of the CMB temperature. There's a second instrument on Kobe that surveyed CMB map. That too was equally stunning. That instrument measured the same temperature of 2.73 Kelvin everywhere, proving that CMB is very isotropic, meaning uniform in all directions. Do you remember I talked about the cosmological principle in the discussion about galaxy distribution? That result of the CMB map demonstrated the same, that the universe is the same in every direction when it comes to CMB, with no preference for any specific direction, okay? And that is consistent with the cosmological principle. However, still, while it may look uniform, we had expected some variations. And pay attention now, because this is where great science and great minds come to work. We believe this because we need some imperfections. The universe cannot be perfect. This may sound funny to you, but 100% perfectly uniform universe cannot form the large-scale galaxy structure we observe today. Regions of slightly different mass density, energy density, and temperature must have existed from the very start in order for some regions to preferentially grow in structure, meaning some regions in space will have slightly higher density, thus continuing to attract more mass over time through gravity and grow more structure and become more clumpy. These inherent variations, however small, must exist, and CMB distribution should also reveal these imperfections. After all, CMB photons interact with matter, and their energy or frequency is directly related to the temperature. Okay, photons, frequency, and energy is directly related to the temperature. In addition, now this may blow your mind even more. From the theoretical front, physicists 100% believe in quantum physics and say that quantum realm with expected quantum fluctuations also means the early universe must be born with the seeds of these quantum variation. That quantum physics is simply unavoidable, and the birth of the universe must be embedded with these quantum variation built in. Okay, and we should be able to see these tiny variations, and amazingly, we do. What you're looking at is the all-sky CMB survey map from Planck surveyor showing lots of detail. Indeed, you can see the differences in temperature. They are tiny, but they are measurable. And we call this CMB anisotropy, meaning there are indeed differences among different directions. Okay? Now, the first generation map from Kobe in early 1990s looks far more blurrish in comparison, but was enough to show the anisotropy. We don't need to go to this Planck surveyor map to be convinced. The early Kobe result around 1990 was enough. The differences in this temperature is very tiny and takes a special so-called differential instrument to be able to map out the differences on the order of 10 to the minus 5, which is 1 part in 100,000. That's how tiny it is, 1 part in 100,000. And so it does take a very good instrument with very special technique to measure this. The original Kobe result of the CMB map also won a Nobel Prize for George Smoot. By the way, I worked for George Smoot for a few months when I was much younger. Now, this map you are looking at is the third generation from the Planck surveyor. Blue is cooler by about 0.00001 lower. Okay, so let me make sure that I said it correctly. 0.00001 lower. And the red is warmer by about 0.00001 higher. Okay, now the coloring of the blue and red is highly exaggerated to display these very minute differences, because if we just use the regular scale and try to show 2.73 and then the variation of 1 times 10 to the minus 5 above and below is just too tiny. You would just see a complete same color, for example, just completely white. Okay, and so without the differential technique for the measurement and also the special coloring effort, the CMB map would otherwise look perfectly smooth with a single color showing perfectly constant temperature across the sky, because 1 part in 100,000 is just, in reality negligible. But we are specifically looking for the tiny differences, so we were digging in. Okay, and again, this is the Planck surveyor CMB map, not the original Kobe's map. Now, one thing to point out is this: we can point the detector to a specific fixed direction. Let me point this out. Instead of an all sky map, we can point the, let's say, just let me draw here. Okay, let's say we just point at this direction right here. I'm pointing across here, a fixed direction, and just to measure the temperature in different wavelengths in just that one point, literally measuring the spectrum of that direction, and we will get a perfect black body spectrum. Okay, and we can do this for every direction, and every direction will show a perfect black body spectrum. But the black body in one direction will shift slightly with respect to another direction, and that's because one point of the sky will have slightly different temperature from another point in the sky. Okay, and so therefore they're black body. Both are black bodies, but they will be slightly different. Okay, so I'm explaining this to you so that you are clear about the nature of the CMB photons. But in reality, to get this all sky map of differences, we use the differential techniques, but not from measuring black body spectra everywhere. Is a completely different techniques. Okay, now in any case, the story does not end with the confirmation of the cosmic microwave background. Okay, it proved what happened in the early universe, but the story doesn't end there, and we will have much more to say next week. Now we go back again to Hubble's law. You have seen this plot many times, so we will not explain this much more. We just go to the next slide. So the question is about the age of the universe. Hubble found the farther away the galaxy, the faster it is moving away from us. And this led to a very straightforward, stunning conclusion, and that is the universe is expanding. And we can use Hubble's constant to determine how long the universe has been expanding, which means essentially the age of the universe. And we start out with the simple kinematic, basic physics. Velocity equals distance divided by time. And then therefore time is also, the travel time is equal to distance divided by velocity. Is just very straightforward algebra. In time, for example, let's say you are driving 150 miles per hour, and that's your velocity. And how long would it take to go 100 miles? Well, then you take 100 miles divided by your velocity, 50 miles per hour. That gives you 2 hours. And now we can think about the same for the Hubble's law, which is velocity equals to Hubble constant times distance. Now, if you're good with mathematics or good with basic physics, you cannot really see where this is going. But let's go through some basic logic this way. Because we know time is equal to distance divided by velocity. Okay, we know it right here. Okay, time is equal to distance divided by velocity. But Hubble's law says velocity is h0 times distance. So you just plug that right here. So distance divided by velocity, but velocity is equal to h0 times distance. And therefore, distance, they cancel out. And then time is just 1 over h0, okay? So look at this again. The travel time, or the time that this is in motion, is 1 over h0. And so the time since that the universe has been expanding is equal to 1 over the Hubble constants. And if you're good with math or basic high school physics, you can easily see from Hubble's law right here, okay, just look at this one right here, that because velocity equals h0 times distance, then h must be 1 over time, because velocity is simply distance divided by time. So h0 must be 1 over time, okay? So Hubble constant is just the inverse of a time, and that time is the age of the universe. The age of the universe then is the inverse of the Hubble constants. A larger Hubble constant will give us a younger universe, and a smaller Hubble constant will give us an older universe. And you can also use this as a question for weekly discussion. Explain why this is the case. It should be straightforward. Now, for a Hubble constant of 22 kilometers per second per million light years, we can very straightforwardly calculate the age of the universe to be 13.6 billion years, which is not bad at all compared to the modern day value that we determined from various other techniques. Okay, we are going to have a long intermission here. And as stated before, it is best that you watch the video Runaway Universe before starting part 2. In addition, reminding you again, this week's lecture and videos provide an overview without much detail. So focus on the big picture, and you should aim to understand these big ideas first before you try to dig yourself down into details. Okay, so please watch the Runaway Universe and come back to part 2. Welcome back, and I hope you have watched the Runaway Universe. We will finish up chapter 22, but we will move through part 2 a bit faster. If you've watched the Runaway Universe, and then you know the effort of astronomers to measure the so-called deceleration parameter of the universe ended up in a huge surprise. We have been assuming a constant rate of expansion, but what if the expansion rate is not constant? What if the expansion rate of the universe is decreasing? If that is the case, then the universe would have reached its current size faster than we think. The universe would actually be younger. If instead the expansion rate of the universe is increasing, then the age of the universe would, on the other hand, be greater. For many decades, we had believed that the expansion rate must be decreasing because of nature of gravity being an attractive force. Thus, gravity will slow down the expansion, eventually pull everything backward, and the universe will end in a big crunch. This is certainly predicted by Einstein's theory of general relativity. Well, sort of, and we will explain more next week. And this has been the standard belief until, well, did you watch the video Runaway Universe? Until astronomers got a huge surprise. I remember this like it was yesterday. A huge shock to the community. It was a huge shock. Using type 1a supernovae as standard candles and many sleepless nights to confirm the measurements and to make sure everything has been done right, the supernova hunters found that the universe's expansion is anything but constant or slowing down. It is completely the opposite. It is accelerating. It was just wild. And we have discussed this many times. Up to date, white dwarf supernovae or type 1a supernovae are the most reliable standard candles for large distances because the physics is very standard, is very well known, is formulated, and the supernovae are very luminous, giving you measurements capable of going to larger distances. So prior to 1990 or so, we believed in a recollapsing universe. Okay, so let's see how that works out. Let's mark the time right now and distinguish the past and the future. And the recollapsing universe looks like the red curve that is just shown. It is the theoretical plot of the average distance between galaxies over time. You see that the average distance increases in the past, but slowing down. And sometime in the future, say right here, like at this point right here, the expansion will stop at the turning point, reaching the maximum average distance. And this is because gravity has finally slowed down and pulled the expansion into a stop. And then the universe will start to shrink, okay? Eventually going backward, becoming smaller, and the universe goes back to a big crunch. This is what we believed in for almost 100 years. And I was taught that in college, in graduate school, okay? And so in this model, it is the Big Bang here, okay? Followed by the slowing expansion and the turning point, shrinking and then faster shrinking right here. And then finally, the big crunch, okay? But the data of supernovae tells a different story. It just was not even close. Now, just to tell you a personal story, I was much younger. It was in for some period, some short period, in proximity of these folks in the video, including Philip Pinko. And I heard of murmurs of worrying about equipment and wrong measurements. It was a scramble for a while. And I personally do not know if they had sleepless nights, but I'm sure they did, okay? But then finally, the issue was settled, and that's what you see in the video. What about a universe with constant expansion on an autopilot, going on a constant cruise, expanding forever? This picture is itself not a realistic one, but a good pedagogical tool to think about this issue. And here you see the blue line showing the average distance with respect to time, and it's a linear growth as it should be. And just look at it, the constant expansion scenario also does not fit the supernova data. Now, there are theories trying to model a constant expansion universe, but long story short, they are also ruled out. Now, let's consider the third scenario, an accelerating universe. And in this model, the average distance between galaxies is becoming larger and larger over time, as marked by the yellow curve. And it is just amazing. It is the most unlikely scenario, in fact, never thought of before, that fits the data. Now, I've been saying that scientists are really smart to think of all possibilities, but I do not think there's any earlier published work on the accelerating universe. Maybe there was, but I certainly do not know about it, or it was never a serious thought on it. This discovery was, in fact, a total surprise to the highest degree. And you can also see the acceleration scenario. The yellow line gives the largest estimate on the age of the universe, close to 14 billion years, okay? Right here. So each scenario gives you an estimate of the age of the universe. And the accelerating universe gives you the oldest universe, 14 billion years, close to it. A couple of things. The supernova data is only 20 years old. We did not know this before. The accelerating universe was a real surprise. I'm sure some of you are only 19 right now, and were just born when this result was announced. So maybe like ancient history to you. But for something of this grand scale, this is very, very recent. And it was 1929 when Hubble expansion was established. But nothing else major for the expansion of the universe had come out for the next 70 years until this. The older techniques were good to measure the principal value of the Hubble constant, but not enough to measure the derivative for it, basically not good enough to measure the rate of change of it. We needed more data to farther distances to see the greater changes, okay? It is only when white dwarf supernova technique became matured that astronomers were able to measure farther out and extracted, okay, the rate of change, and ended up detecting this acceleration, not deceleration, okay? We detected acceleration, not deceleration. Here we go. The acceleration of the expansion of the universe implies the existence of some force that acts to push galaxies apart, but actually it's making the space itself bigger, okay? Not and making the galaxies looking like they are going farther apart, okay? But it's really the space itself becoming bigger. And the source of this force is what we are calling dark energy. Of course, we have no idea what dark energy is. We just know what we had observed. Now, this does not mean Einstein's theory is wrong in predicting a recollapsing universe, and we do not go around tossing out theories that easily. What we believed is the existence of some additional factor that must be a part of the Einstein's theory, which behaves like dark energy, pushing the universe into a state of acceleration. And recall dark matter, we know much more about dark matter than we know about dark energy. Okay, for example, we know dark matter is clumpy like regular mass. Okay, just that we cannot see it as a visible matter. Okay, now there are always people who want to take the other side and proposing theories that would explain their observations. For example, one such theory was tire light theory, which theorizes that the issue lies inherently with observations that the luminosities of distant supernovae are lower than assumed, resulting in an illusion, okay, just an illusion of farther distances. Well, this theory has been debunked, okay? Now, interestingly, tire light ideas resurface here and there throughout the past 100 years, typically by folks who appeared not to like a dynamic universe. Okay, one concept here is the universe has some critical density. I'm keeping this slide here to display this concept as a reference. Critical density is the mass per unit volume that would just be enough to slow expansion to zero at some times far in the future. Okay, but of course, this concept is kind of weird in the case of the dark energy now. Okay, so this critical density was an old thinking, but nevertheless, it is still a number that we can use, and we may use this reference to explain more on cosmology next week. And this is what we currently believe about the energy mass content of the universe, about what is that the universe already made of. As of late 1990, we completely changed the pie, this energy pie, because dark energy appeared. And dark energy became up to 70% of the energy content of the universe. Before, dark matter was mind-boggling enough, but at least we thought we were making progress on it. But then this energy content pie completely shifted and just threw a huge monkey wrench and thoroughly messing up our understanding of our physical principle, our understanding of the universe. All of a sudden, our confidence in our understanding of this universe just shriveled it up, okay? Just completely crashed down to the bottom. Okay, from this slide and on, this discussion goes into a fun mode, like a relaxing coffee shop conversation or an afternoon English tea banter, okay? And if you want to stop here and not watch the video anymore, it's perfectly okay. None of these will be asked on quiz or exam. I point out they are projected outcomes based on what we know today, but they are not wild or blind guesses, and they are not overly philosophical, and still are very intelligent thoughts on what can be possible. And keep in mind, I have said, many crazy ideas, so we thought, have turned out right. So you just never know what is the next layer of truth. The most important thing here is to be rigorous, even pursuing some fantastical ideas. Whatever it is that we are thinking about, however crazy it sounds, must come out of something already well grounded, either theories or observation. We don't just randomly pull fantastical thoughts out of the blue, okay? So these are really good ideas, okay? Now, what about our solar system? How does the story end with our solar system? And actually, we know this quite well. Sun will run out of nuclear fuel in about 5 billion years, okay? But the fantastical thought is, but maybe, hope for Earth, maybe, Sun will lose mass and planet could move into larger orbits. Possible, but don't pin your hopes on this. Or it is so many billion years later, maybe you don't care. But that's a possible outcome. There are many scenarios on the end of life on Earth, such as natural extinction events, okay? Now, who knows which one occurs first? But I've heard from geologists that Earth's interior has a heat source, generating much heat to sustain life on Earth. The consequence of this cooling will end life on Earth even if sun continues to shine, okay? The estimate of this timescale is 3 to 4 billion years, but not entirely set in stone, and likely before Sun reaches the giant stage. And so there is literally a possible end to the end of life, not related to the Sun, but because of Earth itself. And onto larger scale, our Milky Way will merge with Andromeda to form Milkomeda. In fact, this larger system will also very likely absorb all other nearby smaller galaxies anyway. But be assured that if we are still in existence, our solar system is very unlikely to bombard with another star. The interstellar distance is just too huge for the star collision probability to be effectively zero. We can use physics to make some predictions about what will happen to our universe in the far future. Using what we know now, we will end up in a big freeze scenario. If the expansion of the universe continues to accelerate slowly as it is now, galaxy and galaxy clusters will remain gravitationally bound far into the future. Eventually, star formation will end as all available matter, material, visible matter, gets caught up in planets, brown dwarf, white dwarf, neutron stars, and black holes. Basically, all star formation will go through their cycles and eventually ended up in these compact dead objects. Okay, in about 1 trillion years, the longest lived stars will run out of nuclear fuels and galaxies will go dark. And let me explain this. The accelerating expansion of the universe is ripping objects farther away from one another, right? But this is happening on the galactic scale or large regions of galaxy, where the impacts of increasing expansion can have effect. Locally, such as within the Milky Way galaxy, the local gravity will act like a glue, keeping the system together and not be ripped apart by dark energy. Okay, but distance from other scales, from other galaxies much farther away, as we are observing now already, is increasing. This also means over time, galaxy groups because they're over larger distances, okay, will become increasingly farther away from one another, and each group will become increasingly more isolated, right? And farther apart. Eventually, they will be so far apart that no galaxy or galaxy group can see any other, okay? The galaxy bound together by local gravity will continue to attract to one another, going through mergers and so on. And then the star formation will go through its processes and so on. But eventually, there will be nothing else outside to come, and merging will reach its end stages, okay, and galaxy and stars will eventually run out of fuel and go dark, okay. But we are talking about a very long time scale here. Now, exceptions such as collision of these dead compact objects can happen, but they do not impact the fate of the universe or even within the galaxy. And physicists predict that protons have a half-life of at least 10 to the 33 years. That's a long time, but it's not infinite. The way we say it is that proton actually decays. Okay, proton decays. If that's the case, then by about 10 to the 40 years, Earth and all other atomic matter will have disintegrated into radiation and subatomic particle. What we're saying is that matter itself is not forever. Although I have said that elementary particles like electrons and quarks are stable and practically live forever, but that's a relative statement. If we believe in the next level of theory, such as the grand unified theories, and we thoroughly believe in it, then an inevitable consequence is that matter, like proton, okay, has a lifetime. To top it off, even black holes are not immune. They will evaporate. This fantastical idea is due to Stephen Hawking, but I must say, recently the foundation of this theory has strengthened and expanded, looking more and more real. Okay, sounds crazy, but could be true. The largest black holes will last until the universe is about 10 to the 100 years old. After that, the universe will consist of nothing but individual photons and subatomic particles. Now, here's a big statement. If we believe that is true, then nothing new will ever happen, and no events will ever occur that would allow an observer to distinguish past from the future. The universe will simply have reached the end of time. And that sounds just awful. Okay? Sounds awful. Now, if I do not know if I subscribe to this, but I'm showing you this extreme extrapolation of thoughts over the fun coffee conversation we are having now by taking what we know now to the extreme. Right? There are certainly other possibilities that we can think of, but this scenario is based on what we know right now, okay? And it is really the logical consequence of what we know now extrapolated into the extreme future. There are indeed some different and big possibilities we can add to the current findings, and let's go through each. Well, we can have a big rip in which dark energy grows stronger over time, slowly rips apart galaxies and stars, and eventually space-time itself. It's certainly possible. We just need more observation to confirm it. And we could also have a big crunch. If dark energy weakens, okay, and it goes to zero, for example, the regular gravity by matter could prevail once again, slowing down the expansion, pulling the universe back together, reversing the expansion, and ends in big crunch, as was believed for a long, long time. And certainly all this are, just fun thinking about possibilities. But of course, we will have to have more observation over a longer time to know what this is. Who knows how long we need for this at all, because we have no idea what dark energy is doing. Okay? Or the third possibility, we can have a big slurp. A quantum fluctuation could at any moment conjure up a bubble of true vacuum, and the universe will destroy itself from the inside out at the speed of light. Okay, let me explain this again. Quantum physics allow quantum fluctuation of vacuum. This is the vacuum bubble. In fact, many believe this is how our universe was born, and so certainly big slurp is possible. Given the infinite time and infinite space, a high energy bubble just needs to happen once. You do not need to see it as a high probability event. Okay, in fact, this probability is extremely, extremely, extremely low. But it is certainly not zero by quantum physics. And in principle, it is bound to happen. Okay, it is just a matter of when and where. So at times, theories and writing papers are like creating artwork, because often it is done with the knowledge of no possible data within lifetime. And that's just how it goes sometimes. Okay, yet we try our best to think scientifically, okay, about nature, regardless of how crazy it is. But it can also be fun. Like I said, we love to have coffee conversations. When Einstein came up with theory of relativity, the concept of time changed. That time is relative. Different observers under different conditions will observe events and time differently. And this is actually reality. That time, it's not absolute. This is very different from Newton's idea, okay? So there's a whole set of philosophy, not just numbers and formula. There's really a whole set of philosophy and thinking about so many of these little issues about, is our will free? What about time, and so on. There's really a whole lot of such discussions. In our world, we perceive time as flowing past us from a real past to a yet undetermined future, right? We definitely have a sense of time flow, past, present, future. But what is the reality? Einstein's relativity, and let me point this out, we usually mean special relativity, not general relativity, okay? Even though general relativity built in special relativity, but usually we refer to special relativity for this discussion. So Einstein's relativity tells us that time does not flow past a uniquely defined presence. Observers elsewhere in the cosmos or moving at different speeds will construct very different current times, okay? There's no possible objective definition of now, okay? All points in space-times form a static block universe, and you are just in there somewhere experiencing the environment from your perspective. Others see it differently in this block. Now, religious folks have a way of saying, do we have free will, referring to our actions already determined by God. Now, I do not want to mix a religious view with true elements of science. What I would like to say is there is no dependence, and this is a scientific statement based on what we know about our theories. Whatever I do now leading to the next events may simply be two independent events, which in my mind, I think they are linked, forced by my decisions. But in this block universe idea, they are simply independent events occurring in the sequence as perceived by you. Now, there's a second level to this block universe. I do not want to overindulge in any fantastical idea other than just to give you the surface. What I want to say is that the block universe actually provides a scenario for our existence. We can even ask the question, is it possible to have a free will here? But the theory is mathematical, not just random talks. That is the difference. They are interesting ideas, but of course, far from mature. And maybe in the future, a stronger framework will emerge to allow more concrete results. And we do have some other fantastical ideas that may reconcile all these weird views into something that actually is much more understandable and much more acceptable from our reality perspective. And recently, the idea that universe may be a simulation has picked up some steam for real, okay? But the idea of simulation stemmed back way back, but as recently as 2003. One recent simulation idea is from Bostrom, the philosopher, and this idea is called Bostrom's trilemma, not dilemma, but trilemma. And here you see one version, but I think the next slide is better. Bostrom is a philosopher recently became famous for his trilemma hypothesis, and it's very intriguing. This version of the trilemma, which is again worse than a dilemma, estimates some probability to each of the three scenarios. Okay, the simulation scenario, the third one, the simulation scenario is the most probable. And I will not say too much about this and just leave it to you to read on your own if you are interested. I will point out if he is right, then he is brilliant, okay? But this is not really science per se, and that is why I'm not pursuing this due to lack of time. However, I can point out what we can say is that there is the other idea, the multiverse idea that I'm sure you heard of, okay? Because you're watching all these Marvel movies talking about the multiverse, okay? This idea is emerging as a potentially strong scientific idea and is looking intriguingly more and more real. And so, is it really that crazy? Because we probably have already seen some reality of this playing out. So can we test the simulation as scenario? Like in the movie Matrix, if you have not seen it, it's a very good trilogy, okay? Now we can look for glitches, signaling some breaks in the simulated world and possibly some connections to the outside. But this is what is really interesting. And this is my view, and I'm going to give you this as to my injection of this idea. the multiverse idea is definitely well founded in quantum theory. It's not just fancy talks. Okay, there are papers and discussion over this, and it has the same issue, or at least the same kind of characteristic as what we talk about simulations, like the Bostrom. So we can possibly look for other verses through glitches in our observations, and some scientists have talked about this as well. And from what I see, maybe Bostrom's view of simulation, remember, he's not a physicist or astronomer. So what he was thinking about simulation could actually be an abstraction of the multiverse idea. He certainly did not think about this multiverse, but he thought about some possibility, and he's so brilliant in figuring out some of this possibility. But maybe it's because, possibility like multiverse exist. Okay, so maybe. So these are fantastical physical models that people are working on, but as they are built up on known principles, there is some chance that some can be true, and such as the multiverse. And this is end of chapter 19. And keep in mind how the story ends, and after is for intriguing conversations. This is to let you know that progress of science and major breakthroughs often go through these fantastical thoughts at first, and they are part of the progress in human endeavors that are almost never shown in standard teaching for good reasons. But this story will be continued.